Hello, I'm going to give you directions for homework number 4. Homework number 4 is due Tuesday night. So there are 11 problems, and the first 3 problems, problem number 1, 2, and 3, are all about vectors. This is very similar to what we did in chapter 3. Now the vectors are force vectors, so the unit of the vector is newtons, but the principle of how you add them, either graphically or by components, all of that remains the same. So, for example, in the case of problem number 2, in which you have a vector in that direction, and then you have another vector in this direction, and then you have another vector in this direction, then I remind you that to add them graphically, you can always take the vector A, and then you can take B, and you can add B here, and you can take C and translate it, and add it to here, and then the resultant vector, the sum vector, is of course this vector over here. This is the resultant. I'm sure you should be able to do this very well. So let's go now to problem number 4. In problem number 4, we have the first applications of Newton's law. And in this problem, you had a suitcase that you are pulling with a force F, and that force F makes an angle with the horizontal. And what is important is that you move this at constant speed. Constant speed means that the acceleration is 0, so the sum of the forces in the vertical direction is 0, as the sum of the forces in the horizontal direction is 0. And a good way to choose your axis is this. And the only thing that remains is that you have to do a free body diagram for the suitcase. And the suitcase is subject, of course, to its own weight. And this surface pushes up on the suitcase with a normal force. And now you are pulling with an angle. So in here, this force makes an angle here, theta. And because there is a net force F in the x direction, something has to balance the horizontal component of the S force in order for the sum of the forces in the horizontal direction to be 0, in order for the object to move at constant speed. That force is friction. So now you know that this force friction is just the horizontal component of this force. So in problem number 5, now you have a crate that is on the ground, and there is no friction. So if there is no friction, and if you apply a force to it, this force immediately is going to give rise to an acceleration. It's no option. So you can actually calculate what is being asked just from that equation. In problem number 6, this is a question of balance, weight, and it's the following. When you're on a balance and you weigh yourself, this is what happens. This is the balance, and let's say the balance has a weight. Let's say it has a weight small w, and then one comes up here and you weigh yourself, and your weight is big W. So what happened is that the free body diagram for you is that you are being pulled down by the earth with W, and you have a normal force that is exerted on you by the balance. That's the force that the balance reads. That's because it gives you the weight. When you look at the free body diagram of the balance now, it's different. The free body of the balance has its own weight, which is smaller than this one, and also feels the action-reaction pair of this one. So this one, by the third law, acts here. And the ground pushes up on the small mass with another normal force, which is the sum of these two forces. I hope it's clear. Number 7. In number 7, this is the question when you go to a certain very high up in the surface of the Earth. So your weight on the surface of the Earth is G, which is the universal constant of gravitation, times the mass of the Earth, times your mass, divided by the radius of the Earth square. You want half of this weight to be at a certain height. Where that's going to be is when you solve this equation for h. And this equation is easy to solve because this cancels, and then you have to solve for h. And I leave that up to you.